So Ankur introduced me, so let's skip this introduction. Just I want to let you know that my professional focus is application performance improvements through all the means possible, either algorithms exploiting underlying hardware, use a better usage of standard library, better usage of programming language, and better usage of the operating system. What does this mean is that exactly today when we talk about virtual functions, we'll talk how to better use virtual functions, how to create an environment where virtual functions can be used more efficiently. I also write for this software performance blog called Johnny Software Lab. So there is a link here in the footer. Just a second. So this is the link to the blog. If you like reading about performance, this is general C++ stuff, applies to other languages as well, but mostly C++, Rust, since these are running low level. So if you want to learn more about performance, you can go there, and you can follow me on Twitter because I also post the articles I posted on Twitter. Okay. So introduction about virtual functions. I hope, I assume that all people who are here know what virtual functions are. So I won't be explaining what kind of problem do they solve. Generally, they enable flexibility. With virtual functions, you get much higher flexibility. That's the cornerstone of the language. So in C, you don't have them, and it's some tasks are really difficult to do in C. Virtual functions are the basic component of the open-oriented paradigm. Without it, there is no open-oriented paradigms. We know that virtual functions, we have like an intuition about that the virtual functions are slower than regular functions. But if you ask people, responses. So today we'll investigate how, why, when virtual functions are slower, and to what extent are they slower to their non-virtual counterparts. And we will also investigate some strategies on how you can mitigate these problems with performance of virtual functions. Now, the performance price of virtual functions depends on several factors, and we will explain in these talks what those factors are. Okay, first, the topic is, we know what virtual functions are, but the question is how virtual functions work. How do the compilers implement virtual functions? Now, C++ standard does not mandate how virtual functions are implemented, but most compilers implement virtual function in a similar manner. So how are they implemented? Here is an example. Virtual functions are implemented using virtual tables. So non-virtual function, its address is known at compile time. For virtual functions, the address is not known at compile time because it depends on the type of the objects. The address of the virtual function is known at runtime. And that means that when the program is executed, it has to look up the address of the virtual function. Now we have an array of instrument. There is a class called instrument. We have an array of instrument pointers in this array. Now each pointer of instrument points to a different object. One is wind, the second one is percussion, the third one is string, and the fourth one is brass. Now we don't know the address, the exact. We know that each of these objects has a method play, what, and adjust. So there are three methods, but we don't know which implementations are at the compile time. So what does the program do? It needs to find the address of the virtual function. So inside of each, so for each type in the type system, there is a virtual table. So the wind type, the wind class has this virtual table, and it has three entries. The first is pointer to the function play. The second is pointer to the function what, and the third one is pointer to the function adjust. Now at the compile time, the compiler does not know the address of the virtual function, but it does know which entry in the virtual table this information can be found. So it knows that, for example, the what function is the second entry in the virtual table. Okay, now question, how does the lookup go? It goes like this. So we follow the pointer, and then in the object there is this hidden member called virtual pointer, which points to the virtual table. And now we see here that we want to call the method adjust. We know that it is at offset 2. We know the address of the virtual table, so we go to the offset 2 and take this address. So this is the address of the adjust, and then we call that function. So the method is simple, but it involves some indirection. Now, first thing you know when looking at this code is that it must be slower than the non-virtual counterpart. It has to be slower because there are more steps involved. Okay, any questions about this? So you can either ask type on chat or you can join in. Both are fine.
Ivica, just to be clear,
Yes.
the virtual table pointer is there in every object.
Yes, yes. Virtual table is per type. So there is one for each type. Each type has a virtual table, but each instance has a virtual pointer. So and they all point to the same table. So if there is a brass object, all objects of type brass have a virtual pointer that points to the brass virtual table.
Thanks.
So this virtual pointer is not visible in it's visible in GDB. You can look it up and see how it goes. Okay, I guess there are no questions. So let's move on to the next part. Let's do an initial analysis. We know that the virtual functions are more expensive than non-virtual functions, but let's see how much are they expensive. So we have a vector of 20 million objects of the same type. And we compared runtimes for 20 million calls to the virtual functions versus 20 million calls to the non-virtual function. So if the virtual function is short and fast, it will run for 153 milliseconds. If it is a call to the non-virtual function, it will run for 126 milliseconds. If we have a long and slow function, if it's a virtual, it will take 32.09 seconds, but if it's not virtual, it will take 31.84. Okay, what does these number tell us? Well, virtual function versus non-virtual function, there is a small difference, but it's not that big of a deal. Even for the short and small virtual function, they're like 20% slower. For long and slow function, it doesn't matter. This is the error of measurement. So in the overall runtime, you won't gain any performance if you convert your virtual function to non-virtual functions. So the results don't look that bad. There is noticeable overhead for small virtual functions. If the virtual function is large, there is almost no overhead. Now the question is this all there is to virtual functions? And the answer is no, there are more. There is more. Questions about this part? Ankur, questions?
So, when you say small and large functions, what sort of line of code we are looking at?
So small would be like returning one single value, and large we have inside a large loop that does some kind of computation. So I have the source code for this that I use. I didn't put them here, but this is virtual function small is something that does some really small, return some value, just use it to decide how the control flow goes further. And the large virtual function actually does some computations.
Sure,
am I talking, just a question, am I talking too fast? Are you able to follow me?
Yes.
yes.
Actually,
Good.
thing is, I think it's fine.
Okay.
Yeah, I can follow.
Okay.
One question,
Yeah.
how do you perform the analysis? I mean, which tool do you use to perform the analysis?
The analysis. So this is the runtime that uses multi-time. There is this tool multi-time on Linux that you can use to run several times the same program, and then it calculates you the runtime, but also standard deviation and so on. It's a really good tool. Next thing. So we have a vector of pointers. Now you know what vectors are, or arrays in C, but we talk about vector of pointers in this section. So now virtual function mechanism is activated only if you access your objects through a pointer or through a reference. So to use virtual function mechanism, you need to access your object through a pointer. So if you're accessing your object through a pointer, if you're using an array or something like that, then those objects need to be allocated on the heap. They are allocated using new, malloc, or smart pointers. Now, accessing objects on the heap can be slow. Okay, but it will depend, and we'll see how. Okay, we have here two vectors of pointers, and we call this optimal memory layout and non-optimal memory layout. So check this out. This is the std vector of base class pointer, and this is the same thing here. But what happens here? So this is a vector, and these elements are neighbors in memory because they're part of the same vector. Now, with the optimal layout, neighboring pointers point to neighboring objects in memory. So this is the optimal layout. Neighboring pointers point to neighboring objects in memory. We call it perfect layout. If you're lucky enough, you get this layout. And this one below, we call it non-optimal layout. So why do we call it like that? We have neighboring pointers, but they don't point to neighboring objects in memory. Actually, they're just pointing to random chunks of memory. So you might ask yourself, why is this important? What does this have to do with anything? Now, as I already said, accessing objects on the heap can be very slow. It doesn't have to be necessarily mean that it will be slow. And the main reason are data cache misses. Data cache, for those who know, is a small memory inside your CPU that is used to speed up access to the data. So how does that data cache misses impact performance? If the objects are neighbors in memory, we can expect performance improvement. With this, if we are iterating this array, we can see good performance. But if we are iterating from left to right on this array, on this vector, we can expect really bad performance. With this layout, there will be no data cache misses or small amount of data cache misses. With this layout, we'll have much higher data cache miss rate and much lower performance. The problem with the layout is that you cannot control it, at least not easily. You can control it, but not easily. You cannot pick between what kind of layout. We call new, for example, you're calling news in a loop several hundreds of thousands of times, and you get some kind of memory layout. Will it be this one or this one? You don't know. If you have a really small example, which is a small example used just for fun, then you can expect the optimal layout. But if you're allocating memory on a system that has been running for some time, and you can expect the non-optimal layout. So how to fix this? Now, vector of objects is much better for the performance compared to the vector of pointers. The vector of objects doesn't suffer from data cache misses. Let's see an experiment. Let's see how it goes. We have a vector of objects containing 20 million objects. We have another vector of pointers. So there is a vector of objects and there is a vector of pointers. We have a vector of pointers where pointer at location I points to the object at location I. So we have a vector of objects, vector of pointers, and we have a perfect layout, this optimal layout, where pointer at location 0 points at the object at location 0. Pointer at location 1 points to the object at location 1. So this is how we create a perfect ordering. Neighboring pointers point to the neighboring objects. Now we measure the time needed to iterate through 20 million objects by following the pointers in the vector of pointers. So we measure the time, but we don't do it just once. There are several iterations of this experiment. In each new iteration of the experiment, we shuffle the pointer vector a bit. What does this mean? Shuffling means that we take a random pointer and swap it with the 0. And with doing this, little by little we are moving away from the optimal layout to the non-optimal layout. Okay, and we measure the runtime of the program as a function of number of shuffles. So shuffle means swap pointer at position 0 with a pointer at position with a random position. Now, question is how swapping of pointers in array influences the speed axis. We have two functions here. One is called a runtime virtual function, and one is called a runtime. We measure runtime of the virtual function and runtime of the non-virtual function. We want to say, see if the reason why the slowness is not, maybe it's not the virtual function, or maybe it's the virtual function mechanism, but maybe something else. So we have here on the x-axis, we have a number of swapped pointers. And here on the left, on the y-axis, we have the runtime. And you see at the beginning, when the layout was perfect, we get about 200 milliseconds for both virtual and non-virtual function. But as we swap more and more pointers, when we swapped 1 million pointers, so that is about 5% of the array, the runtime begins to become slower, and it gets slower and slower and slower. So initially the code was 200 milliseconds. Now it's 1.5 seconds. So it's 7 or 8 times slower. And the whole reason why this happened are data cache misses. So what is the conclusion? Memory layout is very important for program performance. Worst case in our testing is 7.5 times slower than the fastest case. Now, the slowdown isn't related to the virtual functions themselves. The slowdown is related to the memory layout. If you are going through a memory linearly, sequentially, from 0 to n, then works fine. But if you're jumping around the memory, and this happens when you are following pointers, then this causes data cache misses, and this makes your program slower. Now, in order to achieve polymorphism in your programs, you must use the vector of pointers, because virtual functions don't work without pointers. And this problem will appear much more often in the environment of virtual functions compared to the environment when we're just iterating a vector of objects. So are there any alternatives to the vector of pointers? Yes, there are. You can use std variant with std visitor. It's part of the C++ 17, and std variant allows you to. It doesn't use a virtual function mechanism. It uses duck typing. So it's a bit different, but in terms of performance, you won't see this slowdown because there are no pointers to follow. There is this container I implemented as an experiment. It's called polymorphic vector. It uses virtual dispatching, but doesn't use pointer. Downside is that it increases memory consumption. The last thing, which is probably the best if you can do it, is to have a pair type vector. So there are 4 types, you have 4 vectors. Now there is this boost base collection container, which has support, so it will internally allocate 4 vectors for 4 types, so you don't have to do it. The good things about these pair type vectors is you don't have vector of pointers, you don't have increased memory consumption, but the downside is you cannot sort those objects in the vector that maybe in the way you would like to. Okay. Questions?
Just a question. When you say this vector of objects is having better performance than vector of pointers, is it true for all conditions, or is it depends? Because I recently read in some book where I actually forgot these performance tips when we usually hear depends on the actual system. If you understand what I mean.
The graph will always look like this on all the systems. So maybe the numbers, the runtime numbers will be different, but the graph will always look like this. And when you're just accessing random parts of the memory, it can get really slow. It can get really, really slow. So
okay, thanks.
This graph. So this is the, let's say, the lowest hanging fruit in this talk. If you have a vector of if you are iterating a vector of pointers and you're looking, oh, this is slow, what should I do? Try using vector of objects, some kind of something from this list. It will most likely cause the thing to work faster. So there is these profiling tools. One is Intel's VTune profiler. I think it's the most user-friendly, but it works only on Intel CPUs. But it can tell you if your code has a lot of data cache misses. And if you're seeing that your code has a lot of data cache misses, then you can say, okay, I can try to use something else here.
Okay, thanks.
Okay. Any other questions?
No, I think we can move ahead.
I think we don't have any.
Okay. Next topic or next part is compiler optimizations. Now, compiler knows the address of non-virtual functions at compile time. So it knows the address of non-virtual functions. What this means is the compiler can inline the non-virtual function and avoid a function call. So inlining means that you copy the body of the call and don't do the call. You copy all the commands, statements from the call, but you don't do the call. Now, inlining saves a few instructions on the function call, but that is not all. After the compiler has inline your function, the compiler can perform many other compiler optimizations. Now there are several of them. There are many of them. I'm just saying here two. It can move loop invariant code outside of the calling loop. Loop invariant code is code that inside the loop always produces the same result. So you don't need to run it in the loop. You can move it outside of the loop. The compiler can use special instructions that can process more than one data at a time in a process called vectorization. So vector instruction processes more than one data. It can process 4 integers or 8 doubles. But the compiler cannot generate those instructions if there are function calls. So this can increase the speed from 2 to 6 times. So here's a compiler optimization example. We have this my loop, okay? And we have here a loop that calls this function mysqrt, my square root, and it reads from the array in and it writes to the array out. Now, if you look at this code of the mysqrt, if the bug is true and a is negative, then on the error we print out an error value a is negative. Otherwise, we just return sqrt of a. Okay. Just a second. Now there is this optimization called loop unswitching. So what happens? If the compiler can inline this function here, so if the compiler can take this function and copy its body here, then it can see that this value called debug, this variable, doesn't change inside the loop. It doesn't change inside the loop. Its value is constant for the whole time the program is running. So you can move the check outside of the loop and generate two versions of the loop. One version of the loop is where the bug is true. So there is no check for this debug. So this is the first version. And the other one where the debug is false. And then you get something like this. Now, there is no check in debug, and the compiler can probably use the vector instructions on this loop and make it much, much faster. So if you're running a debug is true, it will be okay. But if you're running without debug, it will be quite fast because the compiler can do some advanced optimization on this loop, but it cannot do it on this loop. Okay, so this is the power of inlining. Now, we wanted to measure this in an experiment. We want to measure this in an experiment and see how the compiler optimizations with inlining, how do they work. So we have this class called object, and it has these two methods. One is called isVisible, which just returns m is visible, and the other one is called getID3, and it returns MID, which is some kind of method, plus moffset. Now this moffset is static variable. Static variable means that its value does not change. It's same for all the instances of the class. Now here we have a test loop. These test loops go through an array, and then it gets an element out of the array. If the object is visible, it increases the count by calling getID3. Okay. Now let's see what's happened. The runtimes. Now we measure the performance of the non-virtual function, inline and non-inline. So there is nothing virtual here. We just measuring the performance of inlining. With inline, the runtime is 136 milliseconds. The non-inline, the runtime is 242 milliseconds. So the virtual function, the non-inline version is almost the inline version is almost 2 times faster. And this is not only related to the calling of the function, so the instruction that are part of the call, but it's related that if the compiler cannot inline this function, it has to load from the memory this value every time. But if the compiler can inline this function, this value is the same, so it's loop invariant, and the compiler doesn't need to load it every time inside the loop. It can load it just once and use it everywhere. So virtual functions, how does this work with virtual functions? So virtual functions inhibit compiler optimizations. Virtual functions are essentially not inlineable. You cannot inline virtual functions because you don't know their address at compile time. So how can we enable compiler optimization? A solution for this is called the type-based processing, and we already talked about it. So don't mix the types. Each type has its own container and its own loop. So this is the type-based processing. Then the compiler can inline small functions and perform the compiler optimizations. This is already implemented in boost-based collection. And this approach is applicable if objects in the vector don't have to be sorted. Now, you might ask yourself, okay, I'm doing all this work, but what are the benefits of compiler optimization? Will the compiler be able to better perform, to generate more efficient code? And the answer is it's case dependent. Some code profits a lot from compiler optimization, other code does not profit so much. And smaller functions in principle benefit more. Okay, any questions related to compiler optimizations?
Not a question, but just a note that if you are having a vector of different types, it probably doesn't even make sense to sort them.
So it's really case dependent. Sometimes, for example, in gaming industry, they use vectors of unsorted types all the time, and there is this paradigm where they completely switch to non-using virtual functions. They're just using these per type objects, and and because they're doing this, they see less data cache misses. The programmer is running faster. But sometimes you have to they need to be sorted somehow, and you cannot mix them. So it doesn't work if your data needs to be sorted. Okay.
Ivica, on the slide for with the static variable, I guess you said that the static would not change through the loop. That is true only for either a single-threaded application or where concurrent changes are not happening, right? To that.
If there are concurrents, you cannot write code like this. You need to have some kind of lock.
Yeah. Thanks.
Okay. Other questions? Okay. Moving on to next topic. Next topic, I call it jump destination guessing. So how does that work? So to speed up computation, modern CPUs do a lot of guessing. So the CPU guesses something. Technical term for this is speculative execution. So it can guess a lot of things. It can guess if the branch will be true or false. It can guess the jump address of a function and so on. So in the case of virtual function, the CPU guesses which virtual function will get called. So there can be like five candidates, and the CPU will guess, try to guess which virtual function will get called. And when it does, it guesses, and then it goes to the address and starts executing the instructions which belong to the virtual function it guessed. So it goes and starts executing, even though it doesn't know if this instruction will actually be needed. If the guess is correct, this saves time. So you did something and you save time. But if the guess is wrong, the CPU needs to cancel the effect of wrongly executed instructions and start over. And this costs time. So this Canceling the effect and restarting, it costs time, it makes your program slower. Now let's do the experiment. We have 3 vectors of 20 million objects. Sorry. Where is my mouse? The first vector is sorted by type. So we have 20 million objects, and at the beginning we have all vectors of type, all objects of type A, then all objects of type B, then all objects of type C, then all objects of type D. So this is when the vector is sorted by type. The second vector is types in vector are sorted in a predictable fashion. A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. So these are the types. So the types in the vector are predictable. So you can, after seeing the sequence for a few times, you can predict which types will appear later. And the third one is the types in the vector are random. So B, C, A, C, A, C, D, C, B, B, A, C, and so on. So the question is, which one is the fastest? Which one is the fastest to iterate through? So we measured the time needed to call a small virtual function on the 3 types of vectors. And fashion. There you can predict the value. The runtime is about less than 200 milliseconds. But if they are unsorted, the runtime is almost 500 milliseconds. So it's almost 2.5 times faster. So the question is why? And the answer is this jump destination guessing is not working in this case. And the CPU has to revert some instructions it already executed, and that this makes the code slower. Okay, so if the type is sorted in a predictable manner, the CPU can successfully predict the address of the virtual function, and this speeds up the computation. If the types appear randomly, the CPU cannot guess successfully, and precious cycles are lost. Solution to this is type-based processing is one of the solutions. Making it some kind of predictable is also a solution. We talked about type-based processing. I'm not going to repeat it again. This effect is mostly pronounced with short virtual functions. Okay, so it doesn't appear that much with large virtual function because the guessing will take some time, but the virtual function itself, if it's a large one, it will take more time. Okay, questions relate to jump destination guessing.
Just curious how sorting can affect the performance. I don't know if I framed. Yeah.
If you have small virtual function, the CPU can guess the address. It can guess the candidate of the virtual function, and it can execute those instructions that belong to that virtual function. It can execute them earlier. Now, it's a really hardware architecture model. So modern CPUs have a lot of resources, and a lot of resources are just sitting idle. So the CPU uses this, and then they start executing the things that they might need. They are not sure 100% they will need it. So, and this is what we measured in here. So we measure the effect of this. This is successful guessing, and this is unsuccessful guessing of the virtual function address.
We are
I have one question.
to speed up.
Yes.
So how can we force the data to be in a sorted or unsorted manner?
You need to think about that. I cannot tell you. So you need to think about it. That depends really on the application. Sometimes it's not possible. Sometimes you have to have objects of different types, and they need to be in one precise ordering, and then you cannot do anything about it. But many times you can. This per type-based processing, where you have for each type you have each vector. So this works much better. The CPU can do much. It can do much more there. It will do less. It will error less.
Oh, sure. Thank you.
Jairam, you have a question? You can unmute yourself.
So my question is there any place where we can figure out what is the jump guessing algorithm? Where can I get it? And
Sorry,
basically, this helps in spatial locality.
Can you repeat the question? I just didn't get it.
So the jump destination guessing algorithm for a CPU, is it available for understanding?
I don't understand. I didn't get it again. Can you please speak slower? There is some problem with your equipment.
Can I try to explain? He's basically trying to ask if this, how does the algorithm the CPU uses to guess the address of the virtual table, is it available so that you can like tune your code to like better suit the algorithm?
Yes.
I think these are proprietary stuff. So how the guessing mechanism work? So these are proprietary stuff. I don't think the hardware manufacturers are hiding these informations. I know that they can predict quite a long sequences of sequence of hundreds. If it's a repeating sequence with hundreds of different objects, he can detect it. But a rule of thumb would be, if you can predict it, then the CPU can predict it. Okay. I mean, there are some.
So
Yes.
is this only possible for C++ objects, or this is possible for any programming language?
So I would think that if it, okay, I honestly I didn't test on Java such languages. Java has a large overhead because of its virtual machine, so it might happen that the time you save is not that visible, because there are other things that are working there behind the scenes that you're not aware of. But every language every language feature that needs to guess something and that it can guess wrong will have this kind of or you can observe this kind of behavior. So if you have Rust, and I don't know if Rust has virtual functions, but if it has them, then you can see something like this.
So just want to add a little bit from hardware perspective here.
Mm-hmm.
Yeah. So see, if you think from hardware perspective, hardware doesn't have virtual functions and anything like that. What it has is like a call to a function. So it's like a jump instruction, might be conditional or unconditional. So what does hardware does? There are multiple techniques. So one of the very simple technique is, for example, this is a PC, and when this PC is there, and then I have executed this instruction 5 times. Out of 5 times, 3 times it jumped or it took a jump, and 2 times it doesn't took a jump. So it just guesses ki now okay, 6th time it will also take a jump. So sometimes based on the condition, for example, the unconditional jumps are like you can 100% predict what it will be. Still it is called as a prediction, but there will be some jumps where hardware will be able to predict it only around 95%. If hardware is predicting below, let's say 95%, and that they will always add up some extra buffers and collect the heuristics there, so that to make it almost greater than 95%. So this is what I can share one document, which is a generic document about how microarchitecture predicts this branches and that. So I will share on our group, Discord group.
Yeah, so these are these are really hardware related. So these are really hardware related details. But again, I mean, you don't need to go that deep. If you as a person can predict the sequence, then probably the CPU can predict it as well. Other questions?
Just to mention, Rust also has a keyword called dyn, dyn, which specifies that this object is not, the type of this object is not known until runtime, but I'm sure that this object implements this class, or this object has the members of this class. So the way it works is you don't have a virtual table, but you have 2 pointers. I was just reading this, that one pointer is the pointer to the actual object, but in Rust, the vtable is not stored in the object. You get a second pointer, which is the pointer to the vtable of that particular type. And then if there are data member accesses, they go through the pointer to the object. If you are calling a virtual function, they go through the virtual table.
Okay. Okay, I mean it's okay, different implementation. Probably in C++ you can get some similar implementation as well. But what does it say to you is that you will have the same effect on Rust if you use that kind of functions on Rust.
Yes, the difference is only that you need to explicitly mention that it is a runtime object, which have different types. In C++, by default, you can, if you mark a function virtual, you'll by default get a virtual call.
Yeah. Okay. Other questions? Okay. Moving on
Go
to
ahead.
the last. Sorry?
Yeah, we can go ahead.
Okay. Moving on to this is I think this is the last part. So it's called, I call it instruction cache evictions. So there are a lot of unknown terms here. So let's explain them. So modern CPUs rely on getting, so I said get to know the instructions they're executing. So this code has been already, the code that the CPU has already executed is called the hot code. So the instructions that have been executed are hot instructions. So what are the properties of hot code? Its instructions are in the instruction cache. Again, instruction cache is inside CPUs, a small memory that helps speed up access to instructions. And if your code is hot, its instructions are in the instruction cache. Its branch predictors know the outcome of the branch. So if you have branching, the CPU knows how that code behaves. Is it true or false? The jump predictors know the target of the jump. Jump predictors are used for virtual function dispatching. So they know the target of the jump. So what happens? CPU is faster when it is executing hot code compared to executing cold code. It is faster. And this can be measured. The CPU's memory is limited. So CPU has limited size of these instruction cache buffers, branch prediction outcome buffers, jump prediction outcome buffers, and so on. So it has a limited memory. And what does that mean is that the code that is currently hot will eventually become cold unless we execute it frequently. So if the code, if your CPU is executing a loop for some time, like 20 million objects, the instructions that are part of the loop will eventually become hot, but everything else will eventually become cold until you leave the loop. When you leave the loop, slowly the loop becomes colder and colder, but the code you're executing becomes hot. So the code that is currently hot will eventually become cold unless executed frequently. And now what? Virtual functions, especially large virtual functions, where each object has a different virtual function, mean that we are switching from one implementation to another. So we are moving from one implementation to another. And this means that the CPU is constantly switching between different implementation and it is always running cold code. So because it is constantly switching between different implementation, it is always running cold code. Okay, let's see an experiment. So measuring the effect of the instruction cache eviction is the hardest because it depends on many factors. It depends on the number of different virtual function implementations. If you have a lot of different implementation, your code will be slower. It depends on the number of executed instructions in the virtual function. So if you, inside the virtual function, if you execute many different instructions, this will make the code slower. If the virtual function is small, it's not that the problem, but if it's big, you will see this problem. So just to make sure there is a size of virtual functions, that's the number of instructions inside, but the number of executed instruction is something else. The function can be large, but it can execute only a few instructions. So size of virtual functions correlates to the number of executed instructions, but they're not the same. We are interested in the number of executed instructions. The effect also depends on how sorted the objects in the container. Are they sorted by type? So best case is when they're sorted by type. If you sort your objects like this, then you get good performance. Because when you first time this is executing cold code for A, but then it's all hot code for A, but then B, then C, then D, then you will most of the time maybe executing hot code. So this is the best case when it is sorted by type. Worst case is when it is sorted by type in a round robin fashion. So A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. So this is the worst case. We did the experiment. We have 4 classes: rectangle, circle, line, and monster. We have 4 implementations of long virtual function. So therefore, each of these classes have this long virtual function, which is long, actually takes a lot of time to execute. The long virtual function consists of a for loop with a large if, else, if, else, if, else, if, else block inside it. Now, for measurement, we use 2 vectors with 20 million objects each. One is sorted by type, and the other is sorted in a round-robin fashion. So what do we measure here? We change the number of the size of the if, else block. By doing this, we also change the size of the function. If there is a small, if the if, else block is small, the virtual function will be small. But if the block is large, then the virtual function will be large. And then we compare the time needed to iterate the 2 vectors. Okay, here is the result. This is a relative performance difference between the sorted and round-robin vectors. So it's a relative. Divide the performance of runtime sorted divided by runtime round-robin. And here on the left, you will see the relative difference, and here down on the x-axis, you will see the number of statements in the if block, if, else block, number of different conditions. And you see when the virtual function is small, so the bigger this number, the virtual function is bigger. And you will see initially if they are sorted by type or in a round-robin fashion, doesn't matter. But as the virtual function grows, the performance of the round-robin becomes slower. It eventually becomes 0.6 value of the performance of the sorted function. So in the worst case, the same function took 7.5 seconds to execute on the sorted vector and 12.3 seconds to execute on the round-robin vector. So that's quite an impressive difference. So this phenomenon is not related to the virtual function themselves. So if you have a pointer class, but if you have a pointer to functions and you set this pointer to point to different functions, you will see the same phenomenon. However, this effect is most likely to occur with large virtual functions on mixed type unsorted vectors with many derived types. So this is when it will occur. Questions?
So I have one question. So since sorting will not alter any correctness of the code, so why don't any of the compiler guys have already implemented this? Like, Clang or somebody could have been easily do this kind of sorting at the front end, right?
No, because it cannot do the sorting, because the sorting would actually change the semantics of your program. Your program does not behave the same. You need to do the sorting. You need to do this.
Okay.
Not the compiler cannot do that changes for you because it changes. Your program behaves differently.
Also,
Okay.
it might not even be possible to sort the types because it would change the side effects.
Sometimes you cannot sort the types because if you have a list of the runners, if you have a list of types of objects and the first place, second place, third place, you cannot sort that list. You cannot sort that vector. It needs to be in that specific way, or sorted in that specific way. Sometimes you can, but in this case you cannot. So sorting is really powerful. You will see many times if you have like a data and processing, then you sort the vector and wow, it works better. It's really fun. For example, if you have linear search, if you have a linear search, so and you're looking for an element, you have a vector of numbers, and you are linearly going through that vector list and looking for a random number. You will see that linear search is faster. Linear search is faster if you're working with linear search will be faster if you're working with what's called if it's sorted compared to when it's not sorted. It's really funny, and that's happens because when you have a sorted, when you're looking for us in a sorted linked list, you have this if check, if condition something, and then but the condition will always be false, and it's easily predictable. And you have unsorted vector, the conditions are unpredictable. So yeah, it works better. Okay, any other questions?
So we have level 1, level 2, and level 3 caches, right? How does this impact? Like whatever we are discussing is all with respect to level 1 instruction cache, or it also is related to level 2 and level 3?
So this talk hides the complexity of the cache hierarchy. I didn't even mention it. I just said there are data cache. Yes, there are data cache level 1, level 2, level 3, depending on the size of your array. You can see this slower performance with larger data sets and so on. But from this practical point of view as a C++ developer, what you do need to know is that if you have per type processing, it will probably be much faster compared to using virtual functions if you have a hot loop. So imagine you're debugging a problem, your program is not working fast enough, and you located, okay, the problem is inside this loop. And I want to see how I can make it faster. If you have call to virtual functions instead in that loop, and if you somehow manage to replace it with per type vectors, you'll get a significant speed improvement.
Okay, I got that message. Thank you.
Okay. So we're almost at the end of the talk. What is the conclusion? So virtual functions do not incur too much additional cost by themselves. So it's not the problem of the virtual function dispatch mechanism. It is the environment where they run which determines their speed. So the environment is the critical here. Hardware craves predictability. It wants to do same type, same functions, neighboring memory addresses. So if you give the hardware it wants, it will run fast. If you don't give it, it will run slow. If you're using virtual functions casually, it's really difficult to make that kind of code hardware friendly. So in game development, they use another paradigm instead of object-oriented programming. It's called data-oriented design. And one of its major parts is type-based processing. Each vector holds one type only. They can do that in the video games because they have these huge amounts of objects, but they don't need to be sorted. Type-based processing eliminates all the problems related to virtual functions. Data cache misses, compiler optimizations, jump destination guessing, instruction cache evictions. So it's a good approach. On YouTube, there is a talk, I don't know who, I don't remember, but they re-implemented some part of the web engine using this data-oriented design, and they get that the engine now works 6 times faster. Unreal Engine is written using this data-oriented design paradigm. Of course, this approach is not applicable everywhere, but you should definitely have it in mind if you're interested in performance. So if you need to use virtual functions, you need to bear in mind the following. The number one factor that is responsible for bad performance are data cache misses. So if you have vector of pointers, you should avoid them. If you should avoid vector pointers on hot path. Other factors also play their role, but not to a lesser extent. If you're designing your program carefully, you can reap most benefit without incurring too much additional cost. Here are a few ideas how to fix your code with virtual functions related to performance. So arrangements of objects in memory is very important. So it is important that neighboring pointers point to the neighboring memory. So you can achieve this with custom allocators. It's complex, but you can do it. What you can also do is try to make small functions non-virtual. Sometimes that's possible. Most overhead of virtual functions comes from small virtual functions. They cost more to call than to execute. You need to keep the objects in the vector sorted by type. That's it. The end.